All right. Hello, everyone. Welcome to Large Language Model Seminar at Northeastern. Today it's our pleasure to have Chien-Chin Huang here to give a guest lecture. So Chien-Chin is a software engineer at Meta working on the PyTorch Distributed team. So before that, he got his Ph.D. from NYU. He's actually my senior academia brother, advised by Jian Li. He actually pioneered several machine learning systems areas before LLMs, including memory swapping between GPU and CPUs. That was Swap Advisor, and also model parallelism, TOFU, both of which we briefly mentioned in our class. For now, he's primarily focused on distributed training at scale. He has contributed to several projects, including distributed checkpointing, FSDP, we talked a lot about that, and asynchronous TP, and also context parallelism. And for today, this topic is going to be about TorchTitan, and we'll see if this is going to be the future. Now, the floor is yours, Chien-Chin.
Thank you, Tensor. Yeah, so I want to mention a little bit is I joined Meta around 2020. I actually joined PyTorch Distributed around 2022, I guess. Within this between 2020 and 2022, I've mainly focused on I joined AI infra team to focus on trainer development. So I only joined PyTorch Distributed only 3 years. Okay. So today's topic is about TorchTitan. I want to apologize first. This slide is a little bit outdated. It's from probably 1 year ago, and 1 year is forever for machine learning area. The reason I can update it is I can make a new slide, but usually we need to go through some legal policy to make sure we can publish it. So since this slide is already available to share with people, so I will directly use this slide. But I will talk about something which is new, or I will correct the information from the slide. So let's get started. So first of all, models are getting larger, and you can see the first slide is already outdated. It's from probably 1 year ago. It's already pretty outdated. It talked about Llama 2, but right now the one talk about Llama 2 and Llama 3. But we can use this as an example because the trend doesn't change. We have a Llama 2 model of 7 billion, 13 billion, and 70 billion. And the Llama 3.1 has much more larger parameter size from 8 billion to 400 billion. So this trend doesn't change. People still trying to create a large language model. And each parameter can be 16 bytes, depends on what kind of precision. Let's talk about FP32 precision. We actually need a 16 byte for each parameter. Why? First, in the forward part, we need a 4 byte to store the parameter itself. We also need a 4 byte to store the gradient in the backward part. We compute the gradient for this parameter. And finally, we also need 8 billion for the optimizer. Usually it's because we use ADAM optimizer or ADAM-W optimizer. This optimizer requires 2 states, and each state is also 4 bytes. So that's overall we have 16 bytes. Of course, if we are using different precision, we have different number, but this is just some number you need to remember. Usually we times 4 to get the total parameter size we need per parameter. So for the smallest Llama 3.1 is 8 billion. We have 8 billion times 16, then we have 128 gigabytes. And we only count the parameter size. We have not count the activation. And usually, the activation account for more memory size than parameter itself. But we only have limited memory, right? Like for H100, we have depending on which H100, you have like 80 to 94 gigabyte. And that's not enough to actually train a single model. So that's why people actually, almost now, people talk about distributed training. But training large language model are pretty challenging, right? We just talked about we need distributed training, and there are actually several ways to parallelize your model. There are parallelism to parallelize the activation. We have tensor parallelism to parallelize the parameter. We have a pattern parallelism to split your model. We have context parallelism to split your sequence length. So it's pretty complicated. How do you know which one to pick or which ones to pick to combine? So this is very complicated. And even if you know which one to combine, there are other techniques. We just talked about parallelism. There are also activation entry point, quantization. For PyTorch, we have Torch compile. All of these can combine in order to train the large language model to make sure the model can fit into memory. And also, even if it can fit it into memory, you want the performance to be good. So right now, the most popular framework, I'm not sure if you heard this, but the most popular library is Megatron, like from NVIDIA. So many startup company or even large company, they use Megatron and modify it to fit their use case. And why people choose Megatron from NVIDIA is because Megatron has the best performance. Even for today, I think, I didn't check the number, but I think Megatron still has the best performance. But it doesn't stop people from creating new one. Today, we create TorchTitan last year, and NVIDIA is also creating new one. Hugging Face has also one. And what's the reason people are still creating new training library? I think the main reason is the existing solutions are pretty complex. It's pretty complicated and it's not easy to maintain. So for example, if I'm a startup company and I fork from Megatron and I want to modify it to suit our use case, but it's very hard to modify. And why is that? Because Megatron actually introduced this parallelism or quantization or auto optimization into the model code. So basically we mix the model code with the parallelism or any optimization together. So this makes it very hard to combine new technique or like to migrate it to new model because it's actually deep combined within the code. So that's one main reason people create a new training library because Megatron has the best performance, but it's not easy to maintain. So today we are going to talk about TorchTitan, and TorchTitan it's created by PyTorch Distributed team. And our main focus is we want to provide simple and composable, and most important is PyTorch native solution. So I just forgot to mention that one reason people also it's very hard to use Megatron or other training library is because you need to install multiple library. You first need to install PyTorch itself, but you also need to install other library like Megatron itself. It also depends on many other training library or like some low-level library in order to make the training faster. For TorchTitan, we only depends on PyTorch itself. And all the parallelism is built in PyTorch or in other PyTorch native library such as quantization, PyTorch AO. So TorchTitan provides a simple and composable PyTorch native solution to make large language model pre-training easier. And here, like again, this is from 1 year ago. When we talk about only pre-training, now people are talking about post-training or fine-tuning. And many people are already using TorchTitan to do fine-tuning or post-training, or as a piece of the post-training. So it's not just for pre-training, but also for any other training pipeline that require efficient distributed training. So this is a kind of a summarize of the technique we use to build PyTorch. And most importantly, again, I want to emphasize this. You will see me continue to emphasize this. All of these parallelism, all of these techniques are within our PyTorch. We don't rely on a third-party parallelism or like an optimization. So here we list some, almost all the optimization we use. For parallelism, we have FSDP, TP, Tensor Parallelism, PP, which is pipeline parallelism, CP, which is context parallelism. All these 4 parallelisms are in PyTorch. And now that we have expert parallelism, which is missed here, but after DeepSeek is released early this year, we actually also create a expert parallelism to train MOE. We also have other optimizations such as activation checkpoint to checkpoint the activation to save the memory. We also have a Torch compiler, which is a compiler team develop this Torch compiler library to compile your model to make it more efficient. And we have other optimizations such as asynchronous TP to speed up the tensor parallelism, and we have quantization. And we also only talk about like optimization, but in production, in reality, there are other very important techniques to make distributed training successful, such as distributed checkpoint. This is to save your model into, for example, a disk or a distributed file system. We need this because usually training can go like a month or even longer, and your GPU can fail. So you need to make sure you save what you trained so far so that you can recover. And in this here, we also have so-called Torch FT integration. Torch FT is a fault tolerance library based on the checkpointing system. It's integrated early this year. So it doesn't show on slide, but just want to make the audience understand that except for all the optimization, there are also other very important techniques to make a training successful. And the distributed checkpoint or fault tolerance library is a very key ingredient to make the training library very useful. And we actually integrate PyTorch native distributed checkpoint. And another important topic is debugging. So I cannot emphasize how important it is debugging. So think about like you have 128 GPU, which is not very large. People nowadays train with like a 1,000 GPU or even more GPUs. So one GPU actually has a bug. Sorry, one rank or one trainer has a bug and fail, or there's a deadlock. So how can we debug this? There are like 1,000 GPUs log. It's extremely hard to just understand which GPU failed. So PyTorch also provide something called nickel flight recorder. Sorry, it's just called flight recorder. It's not just for nickel. It's for any like communication system. So flight recorder actually record the communication stack trace for each rank. And then you can use this stack trace to understand which rank does not participate in the communication. So this is also a very important technique that make the training system useful. Again, it's in PyTorch, and we just integrate it. So I will briefly go through some of the parallelism, and each parallelism can be like a 1 hour or even longer introduction. So I cannot go through all of them. Just give you some idea of what TorchTitan is and what parallelism TorchTitan integrate. And feel free to ask a question and also look into our GitHub repo. Most popular parallelism before, like 3 years ago when I just joined PyTorch Distributed team. This was distributed data parallel was the only parallelism provided by PyTorch Distributed team. It was most popular parallelism. But the problem of distributed data parallel is it parallelizes the input batch. Let's think about you have a global batch size 16, and you have 16 GPU. Then you can actually divide this global batch into 16 smaller batch, and each one has batch size 1. And then you can let each GPU to pick one small batch to train. This is a distributed data parallel. And there's no communication in the forward, but you need to do a gradient reduction in the backward. So that's the overall design of a distributed data parallel. But FSDP is similar, or like people say it's the same as data parallel. But what is different is it actually shard or like parallelize the parameter. But people usually don't see it as a different training parallelism from distributed data parallel. It's more like a distributed storage. Because when doing the training, you still have the full parameter and compute with a local batch, which is the small batch I just described. The batch is already shard, but the parameter is full parameter, and you perform the computation, for example, matrix multiplication. But when you are now doing the training, when you just like start the trainer, all the parameters are actually distributed across GPU or trainer. And what is special of FSDP is before perform any computation, it first needs to issue an OGator to gather all the parameters from all the GPU. Because like I said, FSDP is still a data parallelism. So FSDP requires 4 parameters in order to perform the computation. So what FSDP do is it will issue an OGator to gather all the parameters before the training. And it doesn't do this like in one shot. It does this one layer by layer. Imagine you have like a 100 layer transformer. Before perform the computation of the first layer, you will issue a OGator to gather the parameter of this layer and then perform the training. After this layer's computation, it will drop the parameter. This is how FSDP saves memory. And the people usually view it as not people, but at least me, I view it as a distributed storage. It's no different from data parallelism. It's just like use a different way to save your parameter. You distribute your parameter to all GPU to store them. And when doing the computation, mathematically, it's the same as data parallelism. So this is FSDP, and now it's one of the most popular parallelism people use. Like it's provided by PyTorch as well. And if you check TorchTitan or PyTorch, you will see there are multiple implementation. We have FSDP1, we have FSDP2, we now have a simple FSDP. So this kind of like reflect what I keep mentioning is PyTorch distributed team, we try to pursue offer some library which is easy to use. The reason we develop FSDP2, one of the reasons we develop FSDP2 is FSDP1 is very hard to use, and also is very hard to maintain. It has very neat technique to make sure its performance is good. But in order to do that, it actually sacrifices the maintainability and the usability. So that's why we invent the FSDP2. But still, like it's very hard to maintain. So we later we combine with compiler and invented this called simple FSDP. And then you can see the variation from TorchTitan's repo. And I want to emphasize, like in the right side is how can we use FSDP. So here you can see that we don't actually embed our code, our parallelism code into the model. That's the major difference between TorchTitan and any other training library. So when people write, for example, Llama 3 or Llama 4 or even DeepSeek in TorchTitan, feel free to check the model code on our TorchTitan repo. You can see that our model code is written as just like a single GPU running this model. There is no communication, there's no parallelism code, there's no any other like optimization code inside the model. And then we take this model and apply parallelism or optimization on top of it. So in the right side, you can see that we have the model, and the model is actually single GPU model, like written in single GPU way. And then for when we apply FSDP2, we just go through the model code. Like for example, here we go through its transformer layer and apply fully shard, which is FSDP2, to each transformer block. And then we get a model which is parallelized. So although this code piece is pretty like short and concise, I want to emphasize is this is the core philosophy of TorchTitan. Is we try very hard to make sure our parallelism or optimization are not model intrusive. And if you look into all our PRs from TorchTitan, you can see that all the review will say, okay, you cannot change the model code, you cannot do this. It's because we want to make sure the composability is good, meaning that when you add a new optimization, it can be composed with the existing model. And it's not model intrusive, so that when people introduce a new model to TorchTitan, they don't need to like copy paste a lot of code and change its model code. Instead, you can just like pull in its original model code and then put it into TorchTitan and follow the step like here to use FSDP2 or even more parallelism. Okay. So this is FSDP2. The next one is Tensor Parallel. So Tansen mentioned like one of our early research when I was in NYU, when I was at NYU, so it's called TOEFL, and at that time we call model parallelism. But nowadays, when people talk about model parallelism, it's more about pipeline parallelism, which divides your model into several submodel and perform the training. And when we call like a model parallelism in our original paper, TOEFL, it's more it's called tensor parallel. So why people invent tensor parallel is because there's a very big limitation of data parallelism, whether it's data parallel or FSDP. Excuse me. So I just use an example like suppose your global batch size is 16 and you have 16 GPU. So each GPU can get one batch, right? A batch size of one. But what if now you have 32 GPU? Are you going to change the global batch size? This is usually not something researcher or training like an infra engineer can decide. It's actually decided by model. Sorry. The global batch size is something like decided by model. You cannot randomly say, okay, because I want to train with 32 GPU or even 1000 GPU, so I change the global base size. It can affect the training accuracy. But unfortunately, if you want to use data parallelism, you cannot um, fit to more GPU if your global base size is smaller than the number of GPU you have. Because the minimum local base size is just one. And there's another reason is although FSDP is good compared to DDP is because it actually distributes the parameter to many GPUs, but it actually needed to perform an OR. And imagine performing an OR among like a 500 GPU or even 1000 GPU. This OR will significantly decrease the training efficiency. So we want to limit the OR range, like make sure it does not like communicate among a large number of GPU. So that's why people start to introduce more and more parallelism. The first one is tensor parallel. Tensor parallel is actually a different parallelism compared to data parallelism. It actually divide the parameter and perform the computation differently from data parallelism. For data parallelism, all the GPU get a different input batch or activation, but the parameter is a full parameter. So you perform the computation equally. But for tensor parallelism, we divide the matrix multiplication, which is, we divide the matrix multiplication linear layer is parameter and perform the computation. So you will actually get a different computation and a different activation. So sometimes you will require the communication in order to get a full activation because your parameter is divided. So imagine you are doing a matrix multiplication and x times y, and y is actually divided. So the result you get is actually not a full result. You either need to use OR or reduce to get the actual result. And unlike FSDP, this communication is actually in a bottleneck. Why? For FSDP, if you remember what I just described, before each layer, you need to perform a OR in order to get the parameter. But you can also do this earlier, which is we call prefetch. When doing the second layer computation, you can actually prefetch the parameter of the third layer. Then you can overlap the communication with computation. But for tensor parallel, you cannot do that. You need the actual computation result, then you can perform the reduction to get the actual activation, and then you can perform the next layer's computation. So the communication is actually in a bottleneck. So people usually don't let the tensor parallelism usually do tensor parallelism intra-node, meaning that it's actually within the same machine, AGPUs, because this AGPU collective communication is faster. So even though it's a bottleneck, it's not like affect the overall training efficiency. So this is tensor parallel, and we also have a sequence parallel, which Tantan just described, and also loss parallel. It's all a part of a tensor parallel. It's just like a tensor parallel is mainly parallelize the linear layer, but a sequence parallel is and the loss parallel parallelize other operator. So again, the right side show you how to use our this tensor parallel and sequence parallel applied to our model. Again, our input is just one GPU model, and we parallelize each layer. And then this can be combined with FSDP as well. And the third one is pipeline parallelism. I'm not that familiar with pipeline parallelism, but you can imagine pipeline parallelism is like partition the, suppose you have like 12 layer and you partition the layer into to different stage, and some GPU train the first stage, some GPU train second stage, some GPU train the third stage, or like you can imagine each GPU only get a few layers of the entire model. So that's how PyTorch parallelism work. It essentially split the model into different submodel, and each GPU only get a portion of it. So it can, of course, reduce the memory usage. Again, why do we need a PyTorch parallelism? We just talk about FSDP limitation. We also talk about TP. TP because it will dramatically affect the training efficiency because its communication is in the bottleneck. So people usually do it intra-node within a single GPU. That means its degree is only like A. So you cannot do it with larger GPU. So people add another parallelism in order to train with more and more GPU. For example, here we are talking about 4K GPU. So people utilize pipeline parallelism when you have thousands of GPU. And then the right side also shows the code, like how we parallelize our model using pipeline parallelism. So all of this can be combined together, and you can see the code from our report. And when we show the code here, it's mostly emphasized it's pretty simple to use our PyTorch native parallelism API. So this slide shows context parallel. I think Tensor is interested in this one, and I'm the author of PyTorch context parallel, so I can talk more about this one. So context parallel is, I usually view context parallel as a data parallelism. It's very similar to data parallelism, but what's different, the major difference is for data parallelism, it's actually partition a batch into smaller batch. For context parallel, it's partition one single sentence or like multiple sentence into subsequence. Let's say you have a sentence like I am from Meta, and this sentence can be divided into I am and from Meta. These are two subsequence. So this is actually the main idea of context parallel. We divide the sequence into several subsequences, and then we can perform the training independently on this subsequence. But can we always perform the computation independently? The answer is no. When perform the attention kernel, we actually need a OR to gather the KV. So you can see the figures here. When doing the attention kernel, you have a Q and a KV. The Q is actually like a projection of the sequence we just described. This is the same for K and V. But when performing this QKV attention kernel, we actually need the full KV in order to make sure the mathematically is correct. So we need an OR of K and V in order to perform the computation. So that's essentially the main idea behind context parallel. So we, in the very beginning, we divide the inputs along the sequence dimension, and we then perform the computation as it's divided along the batch dimension, just similar to data parallelism, without any communication. Until we hit the attention kernel, then we need to perform an OR of K and V. And again, this OR is going to be the bottleneck. So there's a interesting idea called ring attention, which similar to the asynchronous TP. Oh, sorry, I didn't talk about asynchronous TP. But basically, it's like divide this attention kernel into smaller attention kernel and overlap its communication with computation. So if you are interested, you can look up the ring attention paper. So this is context parallel, and it can be used when the sequence is very, very long, and it is usually used in such a case when sequence length is like 128K, people will apply a context parallel to divide the sequence length. So this is how we use our context parallel in TorchTitan. And it's slightly different from other parallelism because it's essentially written in a trainer. So its parallelism code is the usage of this context parallel API is actually in the trainer because it needed to divide the input along the sequence dimension. So I want to skip this one. This is activation checkpoint, which essentially just like drop the activation, and in the backward we will recompute the activation. It's actually implemented from PyTorch core team because it can be used even without distributed training. But we also apply activation checkpoint to TorchTitan to save activation memory. And we also apply torch compile. I will also skip this one. And asynchronous checkpoint. Okay. So I want to talk a little bit about like production ready training, which is the other library. People are very fantasize those parallelism, different parallelism. But in reality, there are other very important topics. And this can also be research topic. For example, the one I'm going to discuss is distributed checkpoint. Especially now we have a post-training, distributed checkpoint become more and more important. Why? For post-training, especially this IO framework, we have first training and then we need to transfer the weight to do inference. So how are we going to communicate this training weight? It's actually through distributed checkpoint. So you can view distributed checkpoint as a mechanism to save or snapshot your current model result. You save your model to a distributed file system or distributed storage. And the performance of distributed checkpoint can dramatically affect the training efficiency. So think about you spend like a month to make sure your parallelism work pretty well, but distributed checkpoint itself can like mess up your work because you need a checkpoint. Otherwise, if a GPU fail, then or if you're like a parameter loss, but its performance is pretty slow. So people spend a lot of time optimizing distributed checkpoint. And we have distributed checkpoint implementation in PyTorch, and we utilize it. And we also have a list called zero overhead checkpointing, and can reduce the overhead. So the idea of zero overhead checkpoint is when we try to save the weight, the parameter, we realize that it can actually be overlapped with the next iteration. Think about, we just finished the iteration 10, and we are going to save the distributed checkpoint. We are going to save the parameter. The traditional way to do this is we pause the training and then save the parameter to the disk. But you can check the training pipeline, and you can realize that the forward and the backward part actually do not modify the parameter. So after iteration 10, when we issue a saving to save the parameter, we can actually continue the iteration 11's forward and backward without affecting the distributed training, without affecting the distributed checkpoint. That's how we overlap the distributed checkpoint with the next iteration. And this actually saves us a lot of time. And this implementation is also in TorchTitan. So overall, there are a lot of techniques, and it's not something like I can talk like in just 1 hour. So I want to summarize is the reason we provide and we want to develop a TorchTitan is there are so many techniques there. We just talked about several parallelism, there's distributed triple, and there are quantization, there are torch compile. So in order to make a distributed training work, there are so many techniques, and it's pretty hard to compose. And usually we need several experts to make this composition work. And the main goal of TorchTitan is we want to provide a simple and a composable library that pull in all these PyTorch native technique and let people to play with it, and let people to use this technique to train their model. So that's the overall idea of TorchTitan. And this year, we actually created an experimental experiment folder in TorchTitan. And many company or some people from other team at Meta actually upstream their interesting idea and interesting work to experimental repo. And we encourage people to actually discuss with us if they have something they want to upstream to the experimental repo. So experimental folder actually contains several things. For example, one thing is it contains some new model people want to TorchTitan to support GPT OSS. So some researcher actually implement GPT OSS and upstream to the experimental folder. And we also have several interesting new parallelism currently inside experimental folder. And Hugging Face, they also upstream their model to experimental folder. So the idea of this experimental folder is just like a LED, not just Meta, but also many other communities or companies or even researcher can provide their ideas to TorchTitan and let people to share and use their idea. So